Chapter 16 will focus on conjugated pi systems. In this video, we'll go over the simplest conjugated pi system, which are conjugated dienes, as well as the electrophilic addition to 1,3-butadiene. The term diene means that a molecule contains two carbon-carbon double bonds. Now we've seen the suffix "ene" before, and "ene" is the suffix for alkenes. And the prefix di means that we have two. So diene just means two alkenes within a molecule. Now there are three main types of dienes, and it all is dependent on where the two double bonds are relative to one another. So we can have a diene where the double bonds are right next to each other. These are known as cumulated dienes, which are also known as allenes. We can have a diene where the double bonds are separated by one sigma bond. This is known as a conjugated diene. And lastly, we can have a diene where the double bonds are two or more sigma bonds away from one another. These are known as isolated dienes. So chapter 16 is going to focus on conjugated dienes. Conjugated systems contain overlapping p orbitals. An example of the simplest conjugated system is 1,3-butadiene, which is this molecule here. It is a conjugated diene and the simplest of its kind. Now, in 1,3-butadiene, all of the carbon atoms are sp2 hybridized, which means they all have one unhybridized p orbital. Now, if we picture a p orbital, we know that it has two lobes and it occupies a space above and below the plane of the molecule. So I'm going to go ahead and draw a p orbital for each one of these carbon atoms. Now we also know that pi electrons occupy p orbitals. 1,3-butadiene has a total of 4 pi electrons. Each of these double bonds is 2 pi electrons. Now all 4 of these pi electrons are capable of occupying all 4 p orbitals within the molecule. So these overlapping p orbitals allow the pi electrons to move back and forth amongst all of them, and it makes this molecule have special properties. Conjugated dienes have different bond lengths than regular molecules. So a typical unconjugated molecule, composed of all single bonds, would have bond lengths of approximately 1.54 angstroms. However, in a conjugated diene, the bond length, specifically of the single bond separating our two conjugated double bonds, is slightly shorter at 1.47. Now we know that these pi electrons are not stagnant. They're constantly moving amongst the p orbitals of all 4 of these atoms. And what that does is it's going to give all of the bonds in the molecule slight double bond character. Now double bonds are shorter than single bonds, and so we can see that with the bond lengths that we do indeed have a bond that has some double bond character. Okay, so in all conjugated molecules, all bonds have double bond character. Conjugated molecules also have different conformations. So we have what's called the S-cis conformation. Now this term S means that the diene can be interconverted by rotation around a single bond. So if we were to rotate around this bond, it would become the related conformation, which is known as the S-trans conformation. Now in an S-cis conformation, the two double bonds are on the same side of the sigma bond that's separating them. Okay, so if we draw a line down the middle of the sigma bond, we can see that our two double bonds are on the same side of it. In the S-trans conformation, we have the double bonds on opposite side of that single bond. So again, if we were to draw a line through our sigma bond, we can see that our two double bonds are on opposite sides of one another. But again, we can rotate around this bond to have the S-cis conformation become the S-trans conformation. Now, in general, the S-trans conformation is more stable. That's because there's less steric hindrance with the carbon atoms involved in the double bond. So if you can see with the S-cis, you have these guys on the same side. There's a bit of steric hindrance that can occur here. In the S-trans conformation, they're further apart. As far as the stabilities of dienes, conjugated dienes are much more stable than isolated dienes. And if we're comparing the two different conformations of our conjugated dienes, the S-trans conformation is going to be more stable than the S-cis conformation. But both of these conformations are much more stable than isolated dienes. There are two main ways to synthesize conjugated dienes. Both of them involve E2 mechanisms. So we can either start with allylic halides, such as this guy here. Allylic meaning the halogen is one bond away from a double bond. And we can treat it with a strong bulky base, such as tert butoxide. The reason we want to use a strong bulky base is to prevent substitution reactions. Now this is an E2 mechanism just as we saw in Chem 226. So what's going to happen is the tert butoxide is going to remove the H that's on the carbon adjacent to the carbon containing the leaving group. It'll come in, remove the H, the electrons will go in the direction of the leaving group and kick off our leaving group in the form of a bromide ion to create 1,3-butadiene. We can also start with dihalides, also using tert butoxide. Now, the reason we want to use tert butoxide in this case with the dihalide is to use a bulky base to prevent alkyne formation. So if you recall from OChem 1, we can also use dihalides to make alkynes. But tert butoxide in this case is going to ensure that we're going to be removing the H's at the very end of the molecule, thus forming a conjugated diene. So again, this is a double elimination reaction. We will have 2 moles of tert butoxide removing each one of these hydrogen atoms and forming the double bonds to make a conjugated diene. We saw in OChem 1 that alkenes are capable of acting as nucleophiles and undergoing electrophilic addition reactions. We can see a similar type of reaction with dienes as well. So we're going to take a look at the electrophilic addition of a hydrogen halide to 1,3-butadiene. Now HX can stand for either hydrogen chloride or hydrogen bromide. So let's go ahead and start by numbering the carbons. Now, there are 2 alkenes that can act as a nucleophile. I'm going to go ahead and choose one of them to act as a nucleophile first. So we'll have the pi electrons come over, grab the H from the HCl, and give the electrons to the chlorine. Now, just as we saw in OChem 1, we will be following Markovnikov's rule so that we form the more stable carbocation. So the H is going to go on carbon number 1, the carbocation is going to go on carbon number 2, which is a secondary carbon and also additionally stabilized by resonance. So we have an allylic carbocation here. Let's go ahead and draw the resonance structure that exists for this allylic carbocation. So we can have the pi electrons come over between carbons 2 and 3, leaving the positive charge on carbon number 4. And this is still a stable positive charge because it is allylic. Now, at this point, we usually see a nucleophile, and in this case, it's going to be the chloride ion, come in and add to the positive charge. Now, since we have 2 different positive charges, one on carbon 2 and one on carbon 4, we have to decide which positive charge is the chlorine going to go to. And the answer is it can go to either one. So let's draw the products that exist if the chloride goes to either carbon 2 or carbon 4. Now if it goes to carbon 2, we end up with the H and the Cl on adjacent carbons. If it ends up on carbon 4, the H and the Cl are on opposite ends of the molecule from one another. So this first molecule is known as the 1,2 adduct, meaning the electrophile is added across carbons 1 and 2. The second molecule is known as the 1,4 adduct. Now both of these products are capable of forming because both of these resonance structures exist with one another. However, we can control the products and determine which one is major versus minor with temperature. And we'll see how that works in just a second. This is an energy diagram illustrating how 1,3-butadiene undergoes electrophilic addition and how we form the two different products using temperature. So starting off, we have our 1,3-butadiene, and our first step in the mechanism is the formation of the carbocation. Now the first carbocation that forms for both products is going to be exactly the same. We have our secondary allylic carbocation. So this is the carbocation that forms when these electrons here are acting as the nucleophile. Now at this point, we have two different paths that can occur. We can either have the nucleophile come in and add directly to the carbocation that immediately formed, or we can have resonance occur and then have a nucleophilic attack. So for our first path, the 1,2 adduct formation, this is going to be the easiest formation, and it's going to require the least amount of energy. Because we have a carbocation that initially formed, we just have a simple nucleophilic attack. We don't have to add any additional energy to have the resonance occur. So the bromide will add here to form the 1,2 adduct. Now the reason that the 1,2 adduct has slightly higher potential energy than the 1,4 adduct is because the 1,2 adduct is a monosubstituted alkene, whereas the 1,4 adduct is a disubstituted alkene. And we learned in OChem 1 that as you increase the substitutions of alkenes, you increase stability, which is the same thing as saying you lower the potential energy of the molecule. So it takes less energy for our 1,2 adduct to form, but it's going to form the least stable product. Now for the 1,4 adduct, we have to input a little bit more energy to allow the resonance to occur. Once that resonance structure occurs and we form the other carbocation, the other resonance structure, then the bromide ion can come in and add, and ultimately we will form the disubstituted alkene. Now these are known as kinetic control and thermodynamic control reactions. With kinetic control, we run the reaction at low temperature, such as 0 degrees Celsius. Now low temperature means that there's less energy available for the second activation energy of the mechanism. As a result, the 1,2 adduct is favored. And the 1,2 adduct is favored because it has that lower activation energy because the carbocation is very easily accessible. So with kinetic control, we think of movement. So once that carbocation has formed, the nucleophile can immediately add. So it's a very quick reaction. With the thermodynamic control, we run the reaction at higher temperatures, around 40 degrees Celsius. So a little bit warmer than room temperature. Now at these higher temperatures, there is more energy available to overcome that second activation energy and ultimately form the 1,4 adduct. Now the reason that the 1,4 adduct has a higher second activation energy is because of the resonance that's occurring. But because of that resonance, we're able to form the more substituted alkene, which is ultimately more stable. Let's take a look at one more example of electrophilic addition to a conjugated diene, and this time we'll use a slightly more complicated example. Now it's important to note that with symmetrical conjugated dienes, such as the 1,3-butadiene, you're always going to get two possible products, either the 1,2 adduct or the 1,4 adduct, the kinetic product or the thermodynamic product. With an asymmetrical conjugated diene, such as this one down here, it's possible to get more than two products. So what we're going to do is we're going to try and figure out how many different products we can get if this conjugated diene reacts with HBr. So let's start first by numbering the carbons. And with an asymmetrical diene, we have to consider the nucleophilic attack by both of the pi electrons in order to see the different types of electrons or the different types of products that we can get. So we'll start first by having the pi electrons between carbons 1 and 2 act as the nucleophile. So they will come over, grab the H, kick off the bromide ion. Now we are following Markovnikov's rule, so we're going to put the H on carbon number 1 and the carbocation on carbon number 2. Okay, so we've created a secondary allylic carbocation. So at this point, we can consider resonance. Now the resonance that will occur, we will have the electrons shift over between carbons 2 and 3. Which will again create a secondary allylic carbocation. Now you want to look closely at these two molecules. If we were to number the second molecule, starting from the right, we would actually end up with an identical molecule where we have a secondary carbocation on that second carbon and the alkene on carbon number 3. So these two resonance structures are actually the same molecule. So we would not get two different products as a result of resonance. You would actually get the exact same product. So we really only have to consider the nucleophilic attack of the bromide to one of these structures. And that will come here to carbon number 2. Okay, so this is one possible product, and this is the product that forms when the first set of pi electrons do the nucleophilic attack. On the next slide, we'll see the pi electrons between carbons 3 and 4 doing the nucleophilic attack. So I've drawn our first product here just so we can keep track of it. Now let's go ahead and take a look and see the products that form when these pi electrons between carbons 3 and 4 do the attacking. So again, they'll come over, take the H, kick off the bromide. Now we have two choices here. The H can either go on carbon 3 or carbon 4, meaning the carbocation can go on carbon 3 or carbon 4. Now, even though these both look like secondary carbocations, carbon 3 is actually more stable because it's allylic. Okay, so if the positive charge goes here, we will have resonance occur. So the H is going to go on carbon number 4, and the positive charge will go on carbon number 3. Okay, so carbon 3 is the Markovnikov product, or Markovnikov intermediate. Now let's go ahead and consider the resonance. So we can have the pi electrons now come between carbons 2 and 3, and the positive charge will go on carbon 1. Now these two structures are not the same, so that means they both would exist, and our bromide ion can attack at either carbon 3 or carbon 1. So we'll have it form here or here. We'll go ahead and draw both of those products. Okay, so we will combine these two products with the one we drew above. We will verify that we have not drawn an identical product. All of these are different from one another. So as a result of this reaction, we have a total of 3 possible products. So with these types of problems, if the question asks you to determine all of the products, it's very important to draw the mechanism. The mechanism is going to be key to giving you hints as to how many products can possibly form.